Hello, we are Metabytes Analytics, metadata plus bytes of food. Our team consists of myself, Pilar, Aichu, Swikriti, and Eddie. And the scope of our project is to predict restaurant ratings using Yelp's 2024 open data set using solely structured metadata as opposed to textual reviews. And so the structured metadata includes things like categories, location, hours, and amenities. This matters because non-textual signals are cheaper to compute, easier to act on, and can help small businesses and marketers improve customer satisfaction. So let's dive into the EDA and data preparation that took place. We combined two data sets, the business and review .json files, filtered them by 2019 to 2022 to keep the most updated and relevant data in the data set. Then we normalized the nested fields, which included attributes, categories, and hours, to one row per restaurant and ended up with 36,261 restaurants and 67 engineered features to start. We then created operational features like total weekly hours, days open, weekend hours, and average daily hours, and stabilized review count. We then expanded attributes into 22 interpretable features, such as if a restaurant had Wi-Fi, outdoor access, wheelchair access, and then also used multi-class fields that were standardized, such as price, which was encoded to 1 to 4, noise levels, alcohol. And then to avoid leakage, which was one of the most important parts of the pre-processing, because if we added the stars in the training data, then it would have been almost perfectly modeled incorrectly. So we removed any star data that would have infringed our results. And then for categories, we kept top 20 cuisines as compact indicators. For geography, we kept long lat to retain signals without a huge city one hot. And then for the methods, how did we model? We applied 4 supervised algorithms and 1 unsupervised one. The unsupervised ones included logistic regression, elastic net, random forest, XGBoost, and then K prototypes clustering included the unsupervised modeling. All experiments were conducted in Python using scikit-learn, XGBoost, and MLflow for model tracking and easily reproducing it. We wrapped pre-processing and estimators in one pipeline, used stratified fivefold, and framed the task as high rated. So this means that if a restaurant was greater than or equal to 4 or other, that's sort of how we identified it. We compared logistic regression, which was used as our baseline. We used elastic net, random forest, again, gradient boosting, XGBoost, and then we tuned hyperparameters such as grid, random, Bayesian that were noted. And then for our evaluations, we did accuracy, precision, recall, F1, and ROC. And then we held out 80 to 20 split. So that was testing and training, or I should say training and testing. And then everything was logged in MLflow as well as GitHub, which is what we use to review each other's Python and test each other's Python as we each sort of worked on different modeling. So that was a recap of methods and data preparation. I will hand it over to my teammate to explain the next part of the project.
Hi, I'm Aichu. To add what Pilar just shared about the EDA, we also examined the correlation between Yelp features and average rating using percent correlation. We found that accessibility and comfort factors like wheelchair access, table service, alcohol, cafes, and happy hour have strong positive correlation with higher ratings. In contrast, fast service traits such as drive-through, fast food, and delivery tend to lower ratings, showing that quick convenience often trade-off with customer satisfaction. Building on those insights, we developed a complete machine learning pipeline that started with data cleaning, feature engineering, encoding, and scaling, followed by model training and evaluation, which were tracked in MLflow. We also perform hyperparameter tuning, adjusting values such as an estimator, max depth, and learning rate to achieve the best balance between accuracy and overfittings. As shown in the diagram, we use simple imputer to handle missing values, one hot and ordinal encoding for categorical and order data, and min-max scalar for normalization. This preprocessing ensures that the data remain consistent across all models. Finally, we train and compare 5 models and evaluate performance and identify which factors most strongly influence yield ratings. We use MLflow to track and evaluate all our experiments. Each run was automatically logged, capturing parameters, accuracy, F1, and ROC-AUC, which allow us to compare models side by side. As shown here, MLflow made our workflow transparent, reproducible, and easy to compare and optimize for the best performing model. We also use random search and draw 3D plot to help us finding the best hyperparameter combination. From our results, XGBoost achieved the highest accuracy at 0.733 and Random Forest had the best F1 score. Uh, Overall, ensemble models perform better than linear one, showing that nonlinear interaction capture gap rating patterns more effectively. For interpretability, logistic regression shows the direction of its features impact via coefficient signs and odds ratio, while 3 models highlight the most important predictors such as review count, price range, operating hours, and accessibility features.
Hi everyone, my name is Swikriti Joshi, and I will be going over the unsupervised clustering analysis. We grouped restaurants without labels using the K prototypes method to find natural clusters. K prototypes is a good fit because it handles both numbers like hours, review counts, and location, and also the categories like amenities, price range, and cuisine. Using the elbow method, we chose 3 clusters: a simple 2D PCA plot that showed these groups are clearly separated. Most restaurants fall into cluster 0 and 1, about 16,000 each, while cluster 2 is smaller, of about 2,000. We also explored restaurant archetypes to complement our supervised models. We used K prototypes clustering to find natural restaurant groupings. This method allowed us to explore patterns among restaurants based on both numerical and categorical features, revealing operational archetypes that corresponded to different satisfaction levels. Using an unsupervised K prototype clustering model, we grouped restaurants based on both numerical and categorical attributes. To make sense of each cluster, we used categorical lift analysis, which helped us see which features stood out most within each group. From this, we discovered 3 clear restaurant archetypes. Cluster 1 includes high rated family casual places that are accessible and comfortable. Cluster 0 represents mid rated social dining venues, the kind of places with alcohol service and casual vibes. And Cluster 3 captures low rated upscale dine in restaurant that offers premium features but don't quite meet expectations. Overall, what this tells us is that comfort, accessibility, and reliability matters more to customers than luxury features. Thank you.
Hi, this is Eddie. So, our results show that structured metadata alone can predict ratings. So, no review text is needed. This lets owners act on operational levers directly. The overall ROC-AUC is approximately 0.79. XGBoost had the top accuracy with 0.73. Random Forest, the best F1, with 0.65. This is evidence that nonlinear interactions among price, amenities, and hours matter. Higher ratings align with amenities and accessibility, Wi Fi, table service, wheelchair access, dog friendly, while fast service markers like fast food, drive through, extended hours turn lower. So, bottom line, Metadata alone predicts ratings. Ensembles perform best. XGBoost with the accuracy of 0.73. Random Forest F1 is 0.65. ROC-AUC with an approximate of 0.79 because they capture nonlinear effects of price, amenities, and hours. For owners, simple operational tweaks like having Wi-Fi, accessibility, reliable hours, ambience, it offers quick wins. And yeah, I guess that's it. Thank you for listening. We are proud of how this project combines technical modeling with practical insights. You can find more of our code and visuals on our GitHub repo, which is here. We'd be happy to answer any questions about our workflow or findings. On behalf of Metadata team, thank you.